Before we start, if you're enjoying these conversations, please make sure that you like or subscribe to Cleaning Up. It really helps other people to find us.
Cleaning Up is brought to you by Capricorn Investment Group, the Liebreich Foundation, and the Gilardini Foundation. Hello, I'm Michael Liebreich, and this is Cleaning Up. My guest today is James DeMuth, CEO of Seurat Technologies. Surat is an additive manufacturing company specializing in 3D printing of metals. So they're trying to decarbonize the manufacturing of all sorts of metal components. And Surat Technologies is a portfolio company of Capricorn Investment Group, and that's the supporter of Cleaning Up. So it's a fascinating story, and let's bring James DeMuth into the conversation. James, welcome. Thank you for joining us here on Cleaning Up.
Michael, thank you for having me.
Let's get started with a little thumbnail of you, because in preparation for this, we had a little chat and it was just so fascinating and in a way relevant because of the whole kind of lasers and fusion angle. So just give us the route. How did you get to be CEO of Seurat Technologies?
Sure. So, I've always kind of been chasing the root of problems, so to speak. Started off in, grad school doing, essentially robotics for, disaster recovery. Found out we need a better energy source. I went into energy, off to Lawrence Livermore National Laboratory after my master's at Stanford. Went into essentially, how do we build a power plant from the National Ignition Facility there, right? We were expecting to get fusion any day when I joined back in 2009. Of course, what are we, 12 years later, 13 years later? We finally got ignition in the recent news back in December. But, we found when working on how do you turn the National Ignition Facility into a power plant, we needed advanced materials, we needed advanced design, we needed advanced geometries, we needed essentially new ways of making things in order to satisfy the really intense needs that the fusion environment places on structures that need to exist within it. And so we came up with an alloy that could, survive the life of the chamber, qualify for shallow land burial, all those other requirements that you need to operate in a nuclear power plant in fusion environments. But the problem is it couldn't be welded. It had all these little oxide particles in it that would float to the surface if you tried to weld it, and you lose all your properties. So we looked for a whole bunch of different techniques that could process it, and one of the most promising ones was a variation of additive manufacturing called laser powder bed fusion. And we were thrilled. It looked like, hey, we could have all of our design requirements met, we could have all the geometrical requirements met, the metallurgical requirements met. The only problem was that it was going to take over 200 years to make one of these fusion chambers using the best of additive manufacturing. And good luck with managing that project. Not happening in our lifetime for many reasons.
Then I'll let you get back to the flow of where you went next from that, but that's just because it was so big, right? And the laser fusion process is a slow process.
It's a 6-meter radius chamber, multiple walls varying from a few millimeters to centimeters thick. You're just talking about a lot of metal. And laser powder bed fusion is known for being really high quality, great geometrical tolerances, great capabilities there, but it's super slow and super expensive. We didn't even get to that cost part of it. Just the slow part of it killed that one for that purpose. But essentially, Surat was started as I was probably in the right place at the right time, the confluence of advanced laser technology, a drive for needing to solve this problem, experts in material science, lasers, optics all around. And, essentially we put our heads together. I'm one of 5 co-inventors on that initial IP for how we essentially solve the scalability problem in additive manufacturing. And that's what we commercialized Surat to make that happen.
And so the technology then you took out of Lawrence Livermore, out of the National Lab?
Yes. Spun it out. Took a little over 6 months to secure a license to the technology. Went out, raised a Series C to venture funding, a little over $3 million. Then, essentially worked on demonstrating various prototypes and milestones along the way. Raised a Series A in the fall of 2017. Raised our Series B in June of 2021, with some follow-on money coming in the beginning of 2022. And now we're out, making it happen.
And in my introduction, I said that one of your investors was Capricorn Investment Group, which is the supporter of this show. Which round did they come in on?
They came in on the Series B in 2021. So they're one of our, their recent lead.
Okay, so you're now, fully up and running as an additive manufacturing technology company. I just want to, before we dive into the kind of how wonderful, of course, yours is going to be the best and the most brilliant and the cheapest and the fastest and so on, and the highest quality. But before we do that, I want to give people a sort of overview, a little bit of the terrain of additive manufacturing, sort of why we do and what are the different approaches, because it's not a completely new terrain. In fact, we hear about people trying to, additively print everything from biological cells to houses. Now, you don't aspire to do all of that, but maybe we can just give a bit of a thumbnail of can you give a definition of additive manufacturing?
Yeah, I mean, at a really high level, additive is, well, it's a little bit in the name, but you're building a part up on a layer by layer process, essentially adding a new layer of material to whatever previous layer of material you've put down. And in that way, you have the ability to essentially have almost complete freedom over whatever the next layer is. So you basically get geometrical complexity for free. Additive has been around for a long time, especially laser-based additive, right? Originally conceived in the 1970s, first demonstrations in plastic in the 1980s, first demonstrations in metal in the early 1990s. And then, patents are around for about 20 years. So, fast forward from 1990 to 2010, in the early 2010s, we got essentially an explosion of new additive companies coming on the market in the field of powder bed fusion. You had it going from 1 laser to 2 to 4 to 6 to 8 to 10 to 12 or more. Over the last 10 years since then, you've had a lot of new capabilities come online, but in the whole, the technology is very, very similar to what it was initially conceived of, 40 years ago. And so there's a lot of room for potential there improvement. And that's just on the laser side. Of course, there's the plastics. You try and pull on that thread a little more.
The reason I'm hesitant, I don't want to jump in because you're on a roll, but you've mentioned lasers. Obviously, we've got the Lawrence Livermore and we've got the kind of laser containment ignition fusion thing. Now you're talking about lasers for additive manufacturing. I want to get into why a laser helps you build something up, because a lot of people would say, well, the laser should be kind of taking things away, blasting things. We'll get back to that, but let's just touch on some of the other ways of manufacturing. There are lists out there. You must have looked at all the other ways of manufacturing when you were, seeing how you could manufacture these parts for Lawrence Livermore, right? I mean, I've got polymerization, material jetting, binder jetting, extrusion, sheet lamination, deposition. Why the laser fusion? How does it kind of beat those things?
Yeah, so there's a lot of plastic-based techniques that are out there, which are plastics, right? And so we kind of initially those are off the table because we're looking to build metal chambers, right? Just from put the fusion hat back on from when I was at Livermore. There's of all the techniques in metal, right? You got different types of binder jetting, you got material jetting, you got a variety of different things where you basically a lot of sinter-based techniques where you lay down a layer of metal powder and then you inject a glue, or you have essentially a metal sort of glue slurry that you extrude. All of those require a subsequent sintering step, and sintering by definition means you're not melting. And so you're never resetting the crystal structure of the metallurgy.
Let me do this. Sorry to jump in, because my audience, I just assume my audience are really, really, really smart, but they don't know even the little bit that I know about the difference. I'm a mechanical engineer by background, so I know what is sintering, what is melting, what is. But perhaps can we just have it in your words? What are these sintering approaches? Because we'll get on to then why yours is different, right?
Yeah. So metals, can have a huge wide range of properties depending on how they're processed. And, when you're talking sintering, what it really means is you have, let's say, a bunch of powder particles. So imagine a bunch of little spheres all packed together. You heat them up, you get them maybe a couple hundred degrees below their melting temperature, and they start to diffuse into each other. So they start to meld together. They never reach 100% density. They get, close-ish, but you end up having a material that is a little holy, and a material that essentially is gummier, it's softer, and it doesn't have the strength that you would if you were to fully melt the material, reset the crystal structure, and allow it to essentially reset itself. And so there's only really two techniques that are out there that do that allow you to get the best material properties. And that's what we focused on, right? So there's directed energy deposition, which is basically think like a big robotic welder. You got a welder on a 6-axis robot. That's the simplest embodiment I can probably give for you for a mental picture. And that's something that, like Relativity Space uses that, right? To make their rockets. It's generally characterized by low resolution, high throughput rate. Right. And you can get pretty good costs in the process too. But if you want higher resolution, then let's say the size of my thumb, you need to machine the parts afterwards. And that can be extensive. It can add a lot of time. It can add a lot of cost. And so there's only so much scalability you can get to with that process. The other way you can do full melt additive manufacturing is by directing an energy beam to a really small spot and get melting, local melting. Essentially, you're doing micro welding, but you're doing it really fast and really high precision. And you can use either a laser or you can use an electron beam, but electrons repel each other. And so you can't pack as many electrons into a really small spot as you can photons into a really small spot. So you can actually get better resolution qualities in a laser-based technique than you can in an electron-based technique. So that really zeroed us into laser powder bed fusion of all those different types.
But what an amazing sort of stroke of fortune, because Lawrence Livermore happens to be, what is it? They say that the LL is like lasers. Just one of the
lasers.
Best places in the world for lasers, and you happen to, or maybe it was the other way around. Maybe because you knew so much about lasers, you decided that this was the leading approach. But
yeah, in true spirit, Livermorons would say, lasers can do anything, whether it's cutting, whether it's adding, whether it's ablating, whether it's changing colors and painting. Lasers can do it all. So why not this?
So now let's get on to this question of how do lasers add, right? Because, I used to read a lot of science fiction when I was a kid, and they clearly blast things out and they destroy them. But how do they add? You were talking about you take a metal. So you're like taking a sort of salt shaker and shaking some salt on top of something, and then you blast it and you melt it onto what it landed on. Is that a broad description?
That's a high level view of it. I mean, we spread. Think of it like this is a very simplistic view. Obviously, it's a lot more precise than this, but take like, a pile of your salt, if you want to work with that, and you take a wiper blade from your car and you spread it across a plate, right? Obviously, you're using much finer powder, you're using metal instead of salt, and you're using a precision blade, but generally the concept is the same. You spread a really fine layer of spherical granular material across a build plate, and then you come back and you hit it with a laser, and you essentially you're drawing your laser like you would a coloring book, filling in a coloring book with a pen.
Right. So this is powder bed fusion. That's the sort of so far so good. There's other people doing that, right?
Right. There's a lot of companies doing powder bed fusion. It's been around again since basic technology since the late 1970s.
And therefore, I'm going to assume that the thing that spreads the particles, the hopper for the particles, the dosing, that's all standard stuff, right?
I'd say it's come a long ways, right? There is a ton of development work that's gone on in in powder-based spreading and manipulation, right? I mean, clearly, the industry has done a lot of work in that, think, granaries, right? They're dealing with powder day in and day out, but it's different. It's like weird shaped, right? And there's all sorts of stuff with the topology and what it looks like, the size, the alloy, all of that plays into how you deal with it and how you manage it. And so, they kind of go hand in hand. First, you want to figure out what's the best you can spread with, then what's the best you can print with. And that might not be what you thought it was, and you iterate. So the industry has done a lot of evolution over time. And I think there's still a ton of potential for improvement, spreading thinner layers, more repeatable layers, faster layers, thicker layers, all of it with the needs of the system that you're working with. So I don't think that the book is closed by any means on that development work.
Where I was going was not to say that the book is closed, but that is not where your special sauce does not come from just being better at spreading the little granules.
Sorry, yeah.
Your
there's
special
a strong
sauce
foundation
is coming from the lasers,
yes.
right?
Yeah, there's a strong foundation in powder spreading that we've been able to leverage and build on, but
right.
There's a ton of potential as well.
Okay, so now tell us what your special is. Okay, we've now got this powder and it's nicely spread or whatever, and you've got a laser. Talk to us about your laser.
Yeah, so the industry that has been around for a long time, right? They have, 1 to 12 lasers or more operating, essentially focusing a laser beam down to a point that's smaller than a human hair in diameter, right? It's this really, really sharp, tiny spot. And they make a little weld pool. They weld the local powder to whatever's below it, generally the previous layer. And then they got to do more than just the diameter of human hair. So they start scanning it around, right? And and turning it on or off as they scan it to create the pattern they're looking to create. 1 laser is good, 2 lasers are better, 4 are better than that, 8, 16, you may name it, right? But when a laser interacts with the metal powder and it's melting it, they're trying to go as fast as possible, which means they're trying to drive the system as hard as they can in a lot of ways, which means more power, more energy, faster movement. This results in not just heating up the powder to its melting point, but heating it up to its boiling point or beyond. And like boiling water makes steam, boiling metal makes what looks like black soot. And so they blow gas to sort of move that soot out of the way so it doesn't interact with the laser beam, because guess what? Black soot absorbs laser light really, really well. And that means your laser loses intensity on the way down to the powder, and then it doesn't melt it. And so you want to have the right intensity in the laser when you're doing your process, so you have good repeatability, good reliability, and so forth. And so it's this crazy dance they have to do today, where every laser produces a soot plume from the weld pool, and every laser needs to avoid the soot plume created from every other laser. And you're doing this all within a really tight, confined volume. It gets really, really complex really fast. And this is one of the biggest issues and barriers for scalability in the technology as it exists today, is the fact that you can crank up the power in a single beam and you can lose resolution, right? That's directed energy deposition. You get weld pools that are the size of your thumb. Or you can add multiple lasers, but then you have system complexity and the system doesn't play nice, right? And so both, because there's trade-offs on both, you get to diminishing returns and nonlinear math in a bad way, where 1 + 1 doesn't equal 2, it equals like 1.5. So our insight was, we said, hey, we want to have high throughput and high resolution at the same time. And guess what? We're really familiar with lasers and how they scale. And as you grow lasers bigger and bigger, the economies of scale get better and better and better. You get nonlinear math in a fantastic way, where 10x improvement in speed is like twice the cost, right? And so you want to leverage that as much as possible. So what we do is we generate this really giant slug of laser energy, very similar lasers to what they use at the National Ignition Facility in terms of, architecture, right? Go figure. Then what we do is the tricky part. We embed a high resolution image into this beam. And this is probably one of the trickiest parts, because it is super hard to pattern high power lasers, because whatever you're using to pattern it doesn't live very long. It blows up, it melts, it explodes, it combusts, you name it, right? It dies is the end of the end of that story. And so how do you have a device that's incredibly efficient? Because remember, every photon means more mass that's produced on the other end, and you want to produce as much as you can for the amount of photons you're putting into the system. You want to have high efficiency. And so you care a lot about that whatever patterning device you're using absorbing very little, and it needs to survive, which also incidentally means it needs to absorb very little. And so the devices that exist today don't really work for that. They have very high absorption. They have very low tolerance for high average power and high peak power. We have both. And we had the insight saying, hey, Lawrence Livermore, I was there at the time, so we knew what they were doing, but they have this device that they're using for doing essentially dynamic beam blocking for their high power lasers in the National Ignition Facility for fusion. Right? They have these big optics. These optics, will have defect sites in them. And if those defect sites see subsequent, repeated pulses of this high power laser energy, those optics will fail eventually. And that's bad, right? It's a huge amount of time for replacing the optics, a lot of expense. I mean, these are like 2 foot by 2 foot by like 6-inch thick optics. They're massive, right? It takes a long time to fabricate them and a lot of cost. So this dynamic beam blocker essentially allowed the scientists at Livermore to essentially say, well, let's prevent light from ever going from that one tiny, tiny spot on the optic which has the defect. And now that optic will never fail by that failure mechanism. And so our insight was like, whoa, you have a dynamic beam blocker that's programmable and it can handle really high power laser light. So what if we were to pattern that, to use that to pattern lasers to do additive manufacturing? And that's exactly what we did.
Can I ask, this dynamic beam blocker, I'm a simple person, so I imagine it as like a kid's kind of lantern. You have those shapes in front of so you're stopping the laser from going through and hitting the bits that you don't want heated at that point. And coming out of Lawrence Livermore, they were stopping the laser from hitting a defect, which presumably would heat up the defect and then cause failure, cracking, whatever. But what is that lantern screen kind of made of? Or is it electronically, is it an electron beam, or is it what is it? Give me a clue here.
So it's of course made from crystals, because why not? And no, it's a special device it's called an optically addressed light valve. And so it's got no internal electrodes. It's got, essentially, we have the ability to apply electric field on both sides of the device. And inside of it is essentially 2 big components, right? There is a what's called a linear electro-optic material, i.e. liquid crystal. And there is a photoconductor, which is the layer that is activatable by a wavelength of light of our choosing. And so essentially we project a pattern beam of low power light of that specific wavelength. In our case, it happens to be blue. And everywhere that blue light hits the device, it activates it locally. And then that means it activates the liquid crystal. And when light passes through a liquid crystal, you can tune it in such a way that its polarization changes. And so you have, let's say, vertically polarized light coming into this, and whatever pattern you embed in this, all of a sudden you've got that pattern in polarization space coming out. So horizontal and vertical polarizations in the pattern that you've prescribed, and you can do it really fast.
Again, sort of correct me if I'm wrong, because I'm at the very, very limits of what I can do here, what I understand. It's kind of it's an optical semiconductor. You're switching it on and off, and it's either passing light through or not based on some other pattern that you're shooting in from a slightly different direction.
Yeah, it's like a spatial optical transistor.
A spatial optical transistor. You see, now I can understand these words. This is good. We're getting somewhere. Now, but you do this, how quickly do you have to change these patterns? Because you're trying to print these components really fast. You don't sit there with this thing either just on or off. You're changing these patterns very. It's called. There was another word you used, which was dynamic, right?
Mm-hmm. Yes. So, right now our first generation machine is 40 hertz. So that means 40 times a second. That's a 25 millisecond cycle time between, different sort of batches, right? Now, the transition time needs to be much faster than that. And we've got obviously a bunch of works in the progress. Our roadmap, which we talked about previously, but just for the listeners here, right? I mean, we're talking going faster and faster and faster by multiple orders of magnitude and speed, and going from 40 hertz to 400 hertz to 4 kilohertz, right? And that means you need to go faster and faster and faster. Your switching times need to speed up, and so how we pull this in and different implementations of it. But what we're looking at is, we've qualified some stuff in the lab for extremely fast switching speeds on this, which we could potentially even be implementing now into our system, even if the overall laser isn't firing that fast. Imagine you don't have to have just one image per shot. You could have multiple images per shot. And each image, by the way, doesn't have to be on or off. It can be grayscale. So you can have any level of intensity in between. If you update the image multiple times during a shot, you can actually have effective heating and cooling of that powder spot, of that voxel over time within an image. And so every pixel can do its own heating and cooling profile. And I'm sorry if we're diving down the rabbit hole. You're a mechanical engineer by training, so I think you understand what we're talking about. But different heating and cooling rates means different material properties within your metal. Metal is hugely impacted by cooling rates, which affect crystal structure, grain orientation, surface finish, residual stress, you name it. And that means we can affect all those different levels of quality without slowing down our system.
Now, the thing you're trying to print is big, but the laser is working on some area of that, and then you're doing really fine work within the area of the laser. Is that correct?
Yes, and it can all be pre-prescribed ahead of time, right? So it's not like you're definitely do computation on the fly for that.
No, there's a program that's loaded and then off it goes and it works away. How big is the laser? What's the sort of diameter of the laser? You've got these pixels within the laser. Just give us an idea. I mean, are we talking about a couple of millimeters? Or are we talking about a few centimeters that you can work on at the same time?
Think about, for steel, broadly speaking, it's material dependent. So aluminum will be 15 millimeters, steel will be 10, tungsten might be like 8 or 9, right? And so depending on the material you're processing and its different, thermodynamic properties, you're going to see different tile sizes that we can address. And so broadly speaking, it's around, let's say 5 to 15 micron pixels within the beam.
Okay. And then how big are the components? And I'm going to come back to, this is all about keeping the same sort of tolerances that you can do already with the fusion bed deposition, but just doing it much faster. So I'm going to ask, how big are these components and how fast can you do them compared to the existing competitors?
Yeah. So, what's interesting about our technology is that we don't care about what pixels are on or off within our beam. And so, it takes the same amount of time to fire a shot, right? It's a slightly different way of thinking about things, and that has pretty big implications. And so when we're printing, it's about, just rough numbers, it's about 20 times faster for a Gen 1 system. So just to put that out there, right? So you have that number in your head. But what we're looking at is, essentially the ability to, when we say quality, we don't just mean tolerances, right? We don't just mean geometrical features. We mean all the metallurgy and dimensional properties together. Our Gen 1 system, we're talking 450 millimeters on a side, cubic volume, so about 18 inches. This is our starting point, and we did that just based on the system architecture and dynamics for the laser system and how it's operating. As we go to subsequent generations of machines, higher rep rates, higher energies for that laser, what we do is we keep the bed size proportional to the average power. So the area of the bed and the average power that's coming in are roughly held constant. And so as we look at our roadmap, right, we're looking at Gen 2 system a little over a meter, maybe 1 to 2 meters on the side. Gen 3, we're talking like 4 to 6 meters on the side. Gen 4, we're talking getting up towards 10 meters on a side. I mean, it starts to get, we start to get very large, but you can only really justify going big when your production rates mean that you can print parts on a meaningful time scale for commercial needs, right? And that's
200 years.
Exactly. I mean, today, if you have, a 10 meter bed and you try and print it with today's systems, it will take you, drum roll, 200 years.
20 times faster is still 10 years, right? So I'm assuming that by Gen 4.
That's Gen 1. Yeah.
Oh, okay.
Yeah. So just obviously, if we go 10x faster for Gen 2 versus Gen 1, it's 10 times faster. If we go 100 times faster in Gen 3 versus Gen 1, that's 100 times faster. So that becomes 2,000 times faster than where we are today when we look at like the Gen 3 machine. And the reason we can do this and we can sort of have this sort of landscape of different generations is because we know how the architecture scales from the laser side, from the machine side, and we can actually map out, if you do this, this is what you'll get, and this is the economic results from that. And so
the scaling between generations, you talked about, it's going to go from 40 hertz to more hertz, right? It's going to pulse faster. Is the laser going to get, and the laser gets more powerful? Presumably it has to, right?
Yep. I mean, going from 40 to 400 means now, 10 times average power. Yep.
And so Gen 1, you said it's a 450 millimeter cube that you could build. If I'm following correct, if I'm keeping up. Does Gen 1 exist? Have you sold some machines? Where are you in the qualification process there?
So we don't sell machines. We build our machines, we build our own lasers, we build our own machines, but then we operate those machines as a contract manufacturer, right? We sell parts to customers. So today, first step in all this is you work with customers to qualify their alloys to all their requirements. You demonstrate repeatability and reliability in your part production, and then you scale up to series production. So right now we are bringing our first, the alpha revision of our Gen 1 machine online. It should be running here, early in 2023, early this year. We've got a prototype system that we've had on the floor that we've been able to do a lot of work on to date, but the first alpha version of our Gen 1 system comes online early 2023. It's the first of 3 machines that's in our pilot plant. Our pilot plant will hold, again, 3 machines, be capable of printing about 25 metric tons of metal a year on average. And essentially those will be, those first few machines will be the first ones to go into series production for customers, being deployed through 2023.
And so you'll be saying that was a very important distinction. You don't sell the machine, you're going to make the parts, you're going to go to some trade show and you're going to put a sign out saying, we can make really complicated stuff for you really cheaply with really high tolerances. What sort of trade show, what sort of stuff? Who are your customers going to be? Which sectors are you going to sell into?
Yeah, so interestingly, we've done 0 outbound to date. We have been inundated with so much inbound demand and need from high profile customers that frankly we're still just fielding inbound, and our essentially our focus is looking at who we have and identifying who should be first, right? What's the pecking order on all that? Because there's different requirements, different status, different volumes, different price points, all that stuff. And so at this point in time, it's who's hungry, who's got the volumes. We're not looking to do prototyping. We're looking to do high volume production of mass produced parts. You qualify the material, qualify the design, and then you make a lot of it. And the problem is you need the price point to be low enough to be able to get to that point. If it's too high, you're ending up in, really low volume esoteric applications, like high-end automotive brake calipers or, specialty fuel injection nozzles in aerospace, right? And today you often only hear about either, you only hear about really high-end parts, or it's medical or aero. And what we're seeing is that given the price points that we're enabling, we're able to expand into different markets like consumer electronics, like automotive, and not just the highest end cars, and in energy. Energy is like aero, but on the ground, right? And so it's got less. They have less. They have more price sensitivity than you might have for something that needs to be up in the air.
And so my impression of this piece of additive manufacturing, pardon me, the very high tolerance, very high quality, I guess low tolerance is what it really is. Very accurate manufacturing in metals. It's generally used when you kind of can't make the thing any other way. You've got some internal structure, or you've got something just so complex, and the client is not that price sensitive. Am I behind the times, or is that accurate?
Yeah. So what we've found, from various industry research as we were getting going, and our sense of the market from just experience over time, is that there is a lot of barriers when you're trying to justify performance for additive, right? You're taking an application and you're having to justify, hey, we want to use an additive approach to do this. We think we can get it to perform better, but you need to invoke, a different design. You need to invoke combining, let's say, multiple parts into one. You need to really pull all the benefits of additive together to justify the super high price of this really, high fidelity part. And while that's great, we think there's a better way to do things. So when we work with customers, we say, give us your parts. We'll analyze them. We'll give you feedback on which ones we should do first. But our targets are parts that essentially we can make cheaper, faster, and more effectively than they can make it by their conventional manufacturing methods for today. And this means we immediately are able to get, from the finance point of view, that finance team online and excited about what we're doing without having to invoke the benefits of additive. All the benefits of additive are an afterthought. They're secondary, right? And they can be used as icing on the cake to take things to the next level. But this allows for acceleration in essentially in qualification, acceleration in adoption.
In a sense, you're not competing with any of the additive manufacturing companies out there. You're going to be competing with companies doing casting and sintering and all sorts of pretty the existing, I don't want to say low tech, but the mass manufacturing technologies.
Exactly. And that's where the market is, right? I mean, the part market for metal parts is like $2.5 trillion today, growing 10% per year. And it's not in additives. It's in machining, it's in casting, and then there's some amount in forging, right? And the market gets bigger as your price points get lower. Go figure, right? Question is, for each of our generations of machines, where do we address what different applications do we address where we make the right margins for the company and the business, and still give a huge advantage to our customers?
You have a kind of holy grail metric. We need to get because there's always, in hydrogen it's $1 a kilo. In solar it was 10. Well, I always think of it as being $10 a megawatt hour. When we get there, it's like, oh, the market opens up. It becomes essentially infinite.
Yeah, I mean, of course, we've got a ways to go. It's a big market. We've talked about this for a while. There is a fantastic price point at $25 a kilo that, that's basically the average price of a car, right? And that means you've gotten the automotive market, right? Or a very, very large portion of it. I think by definition, you've gotten half, right? And so we often talk about that one, but there's tons on the way. You look at the different industries and different volumes. There's many different sort of milestones and sweet spots. Our probably aggressive target is to be hitting $25 a kilo by 2030, right? Of course, there'll be stepping stones along the way. Our initial price is targeted around $300 a kilo for our Gen 1 machine, half that for Gen 2, half that for Gen 3, and so on, right? But again, part of this is what's the right applications and what makes the most sense to grow the market.
If I take away one thing from this conversation, it will be the idea of going off to buy a car by the kilo and saying, well, I can only, I'll walk into my dealer and say, well, I'm sorry, I can't pay more than $50 a kilo and preferably closer to 25.
Yeah, well, $50 a kilo, that'll get you a BMW. If you're 25, that's going to be more like your, your average GMC.
But let's say you've got the Gen 1 and you're at $300 a kilo. Just give us an idea of off the top of your head, a couple of the types of parts, whether it's for a car or anything else. What are we talking about here in consumer electronics or in energy or in automotive? What type of part will it be?
Yeah, I mean, there's a whole variety, right? I mean, for energy generation, you're talking various aspects of parts that were previously cast and then machined. In pretty much all these industries, they were cast and then machined. They might have been cold rolled and then machined, but generally it's a multi-component process. So you've got, turbine blades, you've got, compressor wheels, you've got, wearable housings, you've got, cellular phones, you've got, a whole slew of different components that I think are broadly in those veins. You've got a lot of, oddly enough, plumbing parts. You've got manifolds, things that they could get very complex. There's benefits to it. I mean, obviously, we're not going to not take the markets that additive exists in today. The problem with the markets that additive exists in today is they're small, right? They're low volume. They're not high volume production. And so it's kind of marrying the two. It's taking the benefits of additive to that next level market that I think we're primed and poised to do.
So there's a whole range of different things that I'm imagining. As I say, I'm a mechanical engineer, and there's valve housings and all sorts of stuff that I could see that this could really, the combination of volume and price point, and I can see how you can munch your way through that over time. One question I want to just come back to briefly is, why not just sell the machines? I mean, if you're going to be really good at the technology of the machines, why do you want to get into all that customer service? Customers are a real pain. Let me tell you, they have to qualify things. You have to work with their design teams. It takes years. Why do that? Why not just sell the machines? These are presumably quite expensive, right?
Yeah, so there's a number of reasons for that, right? I mean, you're talking sales cycle. Selling machine, the sales cycle is much, much longer than selling a part because the customer also has to qualify the part on their end. You still have to do the part qualification either way you go. You can't get away from that. And so when you're selling a machine, you've got that embedded in it, plus the high price of the machine in the sales cycle. Our trajectory, our roadmap, we often say, know what you want to be when you grow up, right? When we grow up, our machines are getting bigger and bigger and bigger and more and more and more expensive, which means a longer and longer and longer sales cycle and less customers who can actually afford to purchase them. There's still a huge market for customers that are, wanting mid-sized batches and not just, exorbitantly high batches of volumes of parts. And so that's another part of the equation in there. When we look at selling parts, there's not many customers who are going to be able to buy a $500 million machine, fast forward, a decade or so, right? But everyone's going to want to buy parts at $25 a kilo.
Right. Although, if you look at analogies from other industries, it might be the wafer fab business or the fab business in semiconductors. You do tend to get specialists who produce the machines, and then $500 million machine, if you're just making, I don't know, you're making valves or you're making turbochargers, you don't want to spend that. But on the other hand, going to a specialist contract manufacturer who has got the balance sheet and the capability to buy a machine for $500 million and then run it, you would see yourself as not going that route, but actually continuing to own and manage those machines.
So I think it comes down to what do customers want at the end of the day. Customers don't want a machine. Customers want parts.
Well, if a customer is a contract manufacturer, they might want a machine, right? Because it gives them something else they can make.
But that's not depends on what market you're in, right? Those aren't our customers today, right? Our customers are the people who are producing parts, because that's at the end of the day, the whole point of the machine is not to be a machine. It's to produce parts. We get the best strategic and incentivized alignment with our customers when our machines are as primed and as tuned as best as possible to deliver quality in the parts. And there is such a wide spectrum of parts and materials out there that there's going to be no end to the discovery that's going to happen for how you can print parts better and the modifications that will be necessary on the machine in order to do that. And we see the longest term potential here for us is to be intimately tied into that process, to be able to understand the outputs, feed it back into the inputs, and ultimately deliver the best possible solution to our customers, which we would not have the insight into if we were just doing machine sales.
Okay, there is an implication though. I mean, to use your figure, you said these machines $500 million each. How many of these machines are you going to be running in 10 years? And who are your investment bankers? Because they're going to love you.
They will. There's a lot of money out there that's just looking for a good way to get put to work. And we're happy. We're so happy to provide that avenue and access to make that money, make a return on investment. I mean, broadly speaking, we deploy a part printing factory. We're looking at just a few years for payback, right, on that investment. So the economics are very, very attractive when we're talking about how we're deploying our part printing factories to deliver goods for our customers.
Okay, now, James, I've got a final sort of little set of questions that I want to ask you, which is, this is all fascinating. I mean, I have the mechanical engineering background, so I absolutely love what you're doing. It's tremendous. But, this is a show about leadership in the age of climate change, climate action, environmental. How does this help save the world, the planet?
Yeah, why am I on this call? No, I'm just kidding. We are effectively electrifying manufacturing, right? We're taking a manufacturing industry which has been powered for, eons effectively. Casting has been around for thousands of years. We've taken an industry that has been driven by fossil fuels forever and turning into one that can be energy source agnostic, right? Casting makes up 20% of the global manufacturing market for metal parts. Machining, another example, right? Machining makes up about 45%. So subtractive manufacturing. You take a mill, you take a lathe, you're cutting away material on your part. Most parts that are machined, you're machining 60 to 80% of your starting feedstock material away. And that's material that never need to be made in the first place. Now, you can either have less material made in the first place, which means less emissions, or you can have just more parts made in general, which means more production, which means, more, those parts are being made for a reason to benefit society, right? So either way you go, your amount of emissions per part made, there's a huge potential to do that better. And we see a huge opportunity to enable that potential through our process of what we call area printing. Of course, there's all sorts of other effects, like, our vision is you have a part printing factory deployed at or near a customer site, making parts on demand for customers where they're needed, when they're needed, which means great reductions in supply chain complexity. I think we've all been very painfully aware of all the issues with our supply chain over the last couple of years. So how can we have parts made locally, reshore manufacturing, wherever your shore might be? We're obviously very US focused and centric based on, our technology, a spin out from a national lab. But I think there's this is a global problem. This is a problem that is pervasive throughout the world, right? Getting parts from A to B, they're made half a world away. Why? Let's make them locally. Let's boost our local economies. Let's make that happen. And generally, it's economics that don't allow you to do that, or that incentivize it to be done elsewhere. And we're able to change the paradigm and make it made locally. There's warehousing reduction and so forth. There's a whole list of different ways where we can impact directly emissions. Then you get into the secondary impacts, and this is literally unlimited. You talk about saying, hey, I'm going to take a car, I'm going to take away 10%, 20%, 30%, 40% of the mass. That means it takes that percent less energy roughly to move it from A to B. You can talk about energy generation, right? I'm going to make my turbine blades more efficient so they can operate at higher temperature. I get my overall turbine of higher efficiency. That means I get more energy out per fuel in. You're talking about enabling new technologies like fusion, right? You're talking about all these different things that are possible because you've leveraged the benefits of additive, you've done weight reduction, you've done performance enhancement and so forth. And right now, we talked earlier about, hey, there's all these benefits of additive, we don't want to invoke them, yada, 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 but you invoke them. Today, they're being invoked because they need to be invoked from a cost perspective. Well, that means they're only being invoked for a very small sliver of parts. What if they could be invoked for all parts? And now you suddenly have unlocked design freedom for literally every part that can be made. Everything that's, from our technology perspective, a meltable material. Metals, glass, plastics, ceramics, anything that melts has the potential to be enabled by this. You've dropped the price point of all that to something where, essentially you're seeing pervasive use of this freedom of design. I don't think we have any concept at all for the explosion in applications that we would see when that happens. And frankly, that's probably one of the most exciting things I'm excited about is, where do we go? I mean, you can make steel, a steel structure with an embedded structure within it, lighter, stiffer than carbon fiber, but infinitely recyclable, no fatigue limit, unlike aluminum, right? It can have high temperature, withstanding properties. It's got all the properties of steel, but it's behaving like a different material, right? These are all the things that you can do when you can start talking about embedded structures, meta materials, materials that don't behave like anything that's in existence today, and you have the freedom of design on top of it. Like, our goal is to kind of make hardware production as simple to do and as cheap to produce as it is to write code and software. And when you can do that, there's going to be explosion of capabilities. Energy is going to be a big one that's impacted by it, and emissions and efficiency. But I think we're going to see a load of others as well.
There was an extraordinary sort of evangelical section for what this technology can do, and very persuasive. I'm a sort of prosaic guy, so I'm just thinking, well, what you're really talking about is that brake caliper that right now you can only afford on a high-end Porsche is suddenly going to be available for the low-end car at the same cost. All of the above for $25 a kilo. That's going to be transformational.
Exactly.
And it's very exciting.
Exactly. We don't just want the Bugatti brake caliper. We want the Honda Civic or the Ford Focus brake caliper, right?
And presumably you can do all of the sort of surface treatments and so on in the same passes with the same laser. So you can harden and you can do all that kind of stuff integrated at the same time.
Lasers can do a lot of things. I have to make my colleagues a little more proud, right? Lasers, nothing but lasers. Sorry.
LLNL, Lawrence Livermore National.
Well, there's LLNL, which is Lawrence Livermore National Laboratory, and Lawrence Berkeley National Laboratory.
Okay, so it's lasers, nothing but lasers. But there is one, I have out there in my audience also some people who think that we should not be, the way to solve climate is to consume less. We should degrow. We should just do less. And they'll probably be excited by the idea that you can do things more efficiently, but they might be scared that if you do all these wonderful things for $25 a kilo, that we're going to buy more cars and we're going to make more of everything because it's just become so cheap. And so there'll be what they call a rebound effect, and this won't help the planet at all. Do you worry about that?
I think if the rebound effect is coming, still leveraging, greenhouse gas emitting fossil fuels, and you're making more of it, yeah, you don't want to go in that direction. But you do want to go in the direction where, I don't think we're going to be, as a society, going less in terms of energy consumption. I just think we need to have better sources of energy that can get us to where we need to be, but do so in a sustainable way, right? We are right now not living in an exergy harmony with the world, right? We're not living in a sustainable point of view with how things are going on, right? We are, we're changing things, and we need to figure out how we can, live sustainably. I don't think that necessarily says we need to do less. I just think we need to do different. And I think we can have both, but we need to be smart about it. So it's not easy, but I think there's lots of paths out there, and how do we grow this future? I think it's going to, obviously, it's like how do you eat an elephant, right? One bite at a time. You just need to have the right direction.
You're talking my language. This is continued human progress, continued standard of living improvements, continued health improvements, education, et cetera, but decoupled from the physical impacts of what we're doing on the planet. So on that note, I would love to just thank you for the time you've spent with us. It is an inspiring story. It's a great technology direction. I wish you enormous luck in hitting your Gen 1, Gen 2, Gen 3, Gen 4. And I'm sure that my audience will have enjoyed it as much as I have.
Terrific, Michael. Well, thank you for having me today. It was wonderful to be here with you, and hopefully we can come back someday.
So that was James DeMuth, CEO of Seurat Technologies, one of the leading new players in additive manufacturing, and of course, a portfolio company of Capricorn Investment Group. Please join me for another extraordinary guest at this time next week on Cleaning Up. Cleaning Up is brought to you by Capricorn Investment Group, the Liebreich Foundation, and the Gilardini Foundation.